Welcome to Brain Vision.
This is chapter 27, problem number 62. We're given a circuit in gravitational field, 25 ohms. This one is 10 ohms. The resistance here, the EMF provided by the battery is 120 volts. We have a switch here, and there is a metal bar that is free to move, horizontally sitting. So this is kind of like the top view. And the direction of, from the top view, the direction of the magnetic field is also horizontal, as specified in the problem. So this is B. Then gravitational force, F sub G, is always, into the page, right? Because this is the top view. So now let's look at what other forces acting on this bar when we close the switch. When we close the switch, the battery is going to generate the current, right, flowing through the circuit, and then it's going to come to a junction. And since the resistance of the bar is also given as 10 ohms, the current is going to get split off half when the switch is closed. And as you can see, the direction of the current through the bar is down from this angle. So if that's the case, then F sub B, there is a magnetic force acting on this bar. The magnitude is actually I over 2, right? Because of the junction rule. ILB, there is also a magnetic force acting on this bar. Let's look at the direction of F sub B. So align your thumb with the direction of the current, which is this way down, and then rest of your fingers with the magnetic field, right? Curl your fingers 90 degrees. That you're going to see when you do that, the direction of F sub B is actually out of the screen, right? Out of page. So then F sub B is counteracting with respect to the gravitational force. So when we're writing the net force acting on the bar, then we're going to do F sub G, because F sub B is up. Let's use the convention. If a force is along positive y, let's take it as positive. So it's going to be F sub B minus F sub G equals m times a, the mass times acceleration of this bar from Newton's second law. So then when we substitute for F sub B, it's going to be I over 2 LB minus mg equals m times a. If we divide both terms by m, right, we're going to get the acceleration to be ILB over 2m minus g. Now, what we need to find is what the current is, right? We don't know what I is. We're given L and B and M and obviously G, but we need to figure out what I is. So in order to figure that out, we need to apply Ohm's law, analyze the circuit. Now, first of all, we have two resistors in parallel, and each of the resistance is 10 ohms. So 1 over 10 plus 1 over 10, right? Just the equivalent resistance for the resistors in parallel. 1 over 10 plus 1 over 10 is 2 over 10, but we have to take the inverse of this, right? So then it's going to be 5 ohms. Let's say 1 over Req here equals Req equals 5 ohms. But this is not the total because we have another resistor in series with respect to this Req. So let's call it Req prime. Req prime is 25 plus 5 ohms, which is 30 ohms. And now from Ohm's law, the current flowing through the main branch is going to be equal to the EMF produced by the battery divided by Req prime, the total resistance, right? So 120 volts divided by 30 ohms is going to give us 4 amps for our current. Now going back to this equation, then acceleration is going to be 4 times the length of this bar is 0.85. That's how it's given to us. And then the magnitude of the magnetic field is given to us as 1.6 Teslas. And then we're going to divide this by 2 times the mass. Okay, so mass is not directly given to us, but F sub g is. So we know what m times g is. So that Fg divided by g is going to give us m, right? Fg is given to us as 2.6. So divided by 9.8. Divided by 9.8 minus 9.8 is going to give us the acceleration. So when we plug everything in, I'm running out of space here. So I'm going to put the final answer up here. The acceleration is going to be equal to 0.45 meters per second squared.